We're going to talk about the question remove k digits. The point is not to solve this question, but to understand how to use stack and when to use stack to solve a problem. Let's get started. Given string num representing a non-negative integer num and an integer k, return the smallest possible integer after removing k digits from num. To be honest, the description of this is quite confusing. This is why we look at the input and output to figure out what it means, right? We have a num here, which is 14322219. It's interesting because you see it's giving us a string instead of an actual integer. That's when you know you can iterate over it. So we can remove up to k digits. In this case, you see that the output, the smallest number after removing 3 digits, is 1219. So what did we remove? We removed the 4, we removed the 3, and we removed the 2. Before we go to the next example, we can already take a look at how we should remove digits. One way to do this, what I thought was that we can just remove the biggest digit. Over here is 3, so if we remove the biggest digit, which is 439, then we actually get 1221, which hilariously is bigger than 1219. So simply removing the biggest digit does not work. Okay, now we want to think about why, right? This is because the placement of the digits matters. Even though 9 is bigger than 2, however, the placement of 2 is to the left of 9. So removing 2 brings more value than removing 9. Now we take a look. So what if we remove all the digits from the left first? So if we remove the left 3 most digit, then it would be 2, 1, 4, 3, right? That we remove. Then we would get 2219, and obviously this is bigger than any of the 2 above. So simply removing from the left doesn't work either. We need some sort of decision factor to decide to balance between whether a digit is on the left and the value of the digit itself. So how do you want to create a small number, right? We want all the numbers to be, we want all small values to be on the left, i.e. if possible we want this to be an increasing sequence. What I mean by that is we want 1, 2, 3, 4, 5 instead of 5, 4, 3, 2, 1. Let's try this train of thought on this example. We want to make it an increasing sequence, right? So we have 1. Well, we only have one number, so we don't know. We have 4, okay. 4 is bigger than 1, so this is still increasing. We have 3. Okay, that's not good. That's not increasing. So we're gonna pop 4. So now k equals 3, right? But we remove 1, so now k equals 2. We pop 4. 1, 3, that is increasing. That's still good. Then we have 2. We add 2 here. Well, 1, 3, 2 is not increasing, so we're gonna pop 3. So let's just say now we have only one more to remove. We have 2. Okay, that is still increasing. We have 1 that is no longer increasing, so we're gonna pop 2, and then k is now 0. Finally, we have 9. Although here we see that this 2 is also not increasing, but since k is 0, we don't pop it. Now that we have some sort of algorithm, well, to be honest, I only know about this once I learned the full solution. I was not able to come up with this at all. This is quite big brain, but I think the key breakthrough point is realizing that if we want to make the smallest number, it needs to be an increasing sequence, and that's how you're able to eventually derive to this. Now that we have this algorithm, let's test it with the next example. Let me reset this. We can see that the number is 10200, k is 1. First, let's start. The first number is 1. We only have one number, so it's increasing. At 0, that's not increasing, so we need to remove 1. Since 0 is smaller than 1. K becomes 0. And now we have the next number is 2. 2 is increasing. We had 0. This is now increasing because 0 is smaller than 2, right? But since k is 0, we don't do anything here. Finally, we have 0. We can see that there's a problem here. There's a 0 at the front. So I think once we have some sort of result, we need to also remove the 0 from the front. So move 0 from the front. Okay, now that we have, let's see the next example here. What do we have here? We have 1, 0, and then we have k equals to 2. Let's try our little example here, right? So say we have 1. 1 is by itself, so it's completely fine. We have 0. Well, that's not good. We're going to remove, this is not increasing. We're going to remove 1. So this becomes 1. We're actually at the end of the array. Since this is 0, the smallest value, it says here to remove 2, we actually just return 0. So that works as well. So in an actual coding interview, you will check this algorithm with some more examples you can make up and think about edge cases. For example, does it handle the 0? In this case, we can see that it does handle zeros. What happens if we delete more than we want? Let's do that. Say if we have k equals to 3, right? And then the number we have, the number we have is 1, 2, 3. In this case, you can see this is an increasing sequence, right? In an increasing sequence, we don't need to delete anything because according to our algorithm, 1, that's increasing, 2, that's increasing, 3 is increasing. But over here, we see that we still want to remove 3 numbers. So which 3 do we remove? In this case, we want to remove from the back. So we want to remove the last few numbers because those numbers are the biggest. What do I mean? Let's illustrate this using a bigger example. Say it's 1, 2, 3, 4, 5, 6, right? 4, 5, 6. If we want to remove 3 digits, we can see this is all increasing, so we didn't delete anything in the process. So if we want to remove 3 digits, if we start from the left, then we get 4, 5, 6. But if we start from the right, we get 1, 2, 3, which is a lot smaller. In summary, so basically let's sum up our algorithm here. We want to delete previous numbers to make it increasing sequence. And then we want to remove all zeros from the left, i.e. to solve like this case, we want to remove all the zeros. And we want to remove all numbers from the right. Well, not all, we want to remove k numbers from the right if there are leftover k's. How do we know that we want to use stack? Because that's what we're doing, right? We want to find questions that use a stack. When we were doing our making it increasing, we can see that whenever, say if we have 1, 4, 5, 6, and then we have a new number, so new number that is 2, we want to keep on deleting the previous numbers until we find a digit that is smaller than 2, right? So we want to delete 6, we want to delete 5, we want to delete 4, 1 is smaller than 2, so we're done, and we add 2 to the end. Over here you can see that what works well is that we're slowly deleting from the back of the sequence. This works because a stack allows you to put to the end at 01 time and pop from the end at 01 time. So it's perfect for our need. In future questions, you'll always see that stack is really good for making an increasing sequence. So stack is good for making increasing sequence. It's a technique that is used to solve a bunch of questions, not just this one. Let's take a look at the code I have written here. So we have the function remove k digits. Here we have the num, the string, and then we have k, the number of digits we want to remove. So first we want to construct the monotone increasing sequence of digits. Monotone increasing just means that it can be equal or smaller or equal to, i.e. it can be 1, 2, 3, 4, but it can also be something like 1, 1, 1, 1, 2, because for the 1, 1, 1, they're equal. Alright, so for every digit, we're gonna loop through. For every digit in the number string, while k and the stack is not empty, we're going to check if the back of the stack is greater than the digit. If it is, we're going to pop, and we're going to do k minus equal to 1. To illustrate this, for example, if we have 1, 5, 4, 5, 6, and then we have a 2 coming in, we check, hey, is stack empty? It's not. We check if the back of the stack, is it bigger than the new digit 2? It is. We pop. Is it bigger? It is. We pop. Is it bigger? We pop. It's not. Alright, then we end it. We don't pop. And then we add 2 to the stack. If we have a number like 3, since the back of the stack is not bigger than 3, we just add 3 into the stack. Once we're done constructing our increasing array, we need to trunk the remaining k if there's k that's still left over. If there's still leftover values, we need to delete, right? Otherwise, we just return the original num stack. For example, this is just an operation to delete from the end. For example, if k left over, there's still k equals to 1, right? Then we want to remove this. Finally, we want to remove leading 0. Else strip just means that we're stripping from the left. This will remove any zeros or matching characters. In this case, it's 0 that is from the left. So we have 0, 0, 2, 0, 0. It will strip it. Over here, we're checking. Sometimes it's possible that we return nothing. The strip or join, like the stack is empty, or else strips everything. This is completely possible because say if we have 1, 2, 3, right, from our final stack, and then k we still have left over 3. In this case, final stack will actually be empty. So we don't want to return an empty stack. This will return this because we're not joining anything, right? So instead, we want to return 0 as our result. I think a lot of these questions, when you see some sort of sequence that ask you to match a pattern to create another sequence, what you want to do is to figure out an algorithm that does the job right. And then after you figure out the algorithm, you want to optimize it by picking a data structure that allows you to minimize the runtime. A lot of the time, you can actually use stack. However, I find it that if you don't know that this technique exists, it'll be really hard to come up with it at the spot. That is why I make this video, just to let you know the stack technique exists. It's really good for building monotone increasing sequence. So next time you see something similar that can use a stack, use it. Let's talk runtime. Over here we can see that we're deleting from the back to construct a new array. This is on. Over here we're using the join and we're using a strip. This is also on. This is the confusing part. We have for every digit a number, we do something with the stack. This is a nested loop. We have a for loop on the outside and a while loop on the inside. However, this is still on runtime. The reason is that we're only iterating through every element in the num stack once. Instead of seeing it like this, the runtime of this algorithm is more akin to something like this. If the while loop is on the outside. Because once we pop, we don't have to iterate over that item again. We're only doing a popping action once for every single item in the num stack. Thus, this runtime, even though it's a nested for loop and a while loop, it's actually on.